breath. Yeah, because the only way
Hey
to find the
everyone, welcome
truth
back and
is
let's write some more neat code today. So today let's solve maximum depth of a binary tree. And the main reason I'm solving this today is just for the sake of completion. We have solved harder tree problems before, but this one is on the blind 75 list, so I do want to solve this problem today. And this problem actually has multiple ways to solve it, so I do think it's a good problem to understand of like the fundamentals on tree traversals. We can do it three different ways, and I'm actually going to show the three different ways. There might even be more than three, but I'm going to show you the three main ways. Basically, recursive depth first search, iterative depth first search, basically depth first search without using recursion, and of course, another way is going to be breadth first search. So I'm going to be showing all three today. So the problem is pretty simple. We're given a root binary tree and we want to return its maximum depth. And the maximum depth is defined as being the longest path from the root to one of the to one of the leaf nodes. And basically
close
along
the
that
door.
path, we're counting the number of nodes. So in this case, you can see we have two paths that are of the same length. So from the root down to here, we have 3 nodes. From the root down to here, we have 3 nodes as well. So those are the 2 leaf nodes we have here. We also have a leaf node on the left side, but clearly we see that there's only 2 nodes in this path. So out of all those paths, what's the max length? Of course, it's 3, so you can see that that's what our output is going to be in this problem. So the simplest way to solve this problem is recursive depth first search. Now, what's the base case? We're using recursion, so first let's think of the base case. Obviously, if we had just an empty tree, right? Like what if this was our tree? What are we going to return? Of course, 0, right? The max depth of an empty tree is just 0. What about if we just we're going to return from the perspective of this root node is just going to be 1 plus the max 1 plus the max of the left and right results, basically the max of the left and right subtrees, in which case it was both 0. So of course in this problem we're going to return 1 as the max depth. Now let's look at this more general example that they gave us. So obviously we're going to do the same thing. We're going to get to the root, say okay, we found at least one node, so the depth is at least 1, and then we're going to return the max of the left and right subtrees plus 1. And why are we doing it this way? Well, you can see that we found this node, but now we have subproblems, right? We need to know what's the max path, what's the max depth, and we'll have to search the left subtree and we'll have to search the right subtree. So we're not even considering this node anymore. We're doing recursion. We're looking at the subproblem. What's the max depth of this left subtree? Well, of course, it's just a node, a single node with no children. So of course, the max depth is going to be 1. Similarly, let's do the right subtree. And so again, this is going to be our recursive case, right? We have one node, and from this node's perspective, we're going to run recursion again. We're going to look at the left subtree and the right subtree, both of which are going to return 1. So then, of course, from this node's perspective, we're going to return 2. The max depth of this subtree is 2. The max depth of the left subtree is 1. So now, when we get back up here, we're saying, okay, from the perspective of this node, we're going to return 1 plus the max of left and right. The max is clearly 2. So from this node's perspective, we're going to return 3. The max depth is 3. So let's code this up recursively. It's literally just going to be this line that I just wrote and the base case. And since we are traversing the entire tree, the time complexity is going to be big O of n. The memory complexity is just going to be the height of the tree, which also could be worst case big O of n if it's not a balanced binary tree. So with recursion, we always want to take care of the base case first. So if the root is null, then of course we're just going to return 0. That's the max depth. Otherwise, we're going to return 1 plus the max of what our DFS of left returns, or in this case, it's not DFS, it's actually called max depth. And since we're inside of the function in Python, you have to say self.maxdepth and then run that on the left subtree and also run it on the right subtree. Now, to make this line shorter, I could actually store the result of both of these function calls in variables, but I think this one liner is pretty much good enough. So we're just taking the result of both of these function calls, figuring out what's the max of it. So what's the max subtree's depth of both of the subtrees, and then just adding 1 to it because we know that the current root node that we're traversing is definitely not null. So this calculation will work out. Let's submit it. And of course, I'm showing that I can't even solve easy problems, so it's not called node, it's actually called root. Hopefully you were able to catch that. But yeah, so this is the entire problem. But what if you're an interviewer, or what if you just want to do this for learning purposes? You want to solve this problem without recursion. Well, there's 2 ways to do it: iterative depth first search or iterative breadth first search, and I'm going to show you both of those right now. Now, there's not a lot of benefits to using breadth first search on this problem compared to just doing DFS recursively, mainly that you just don't have to do recursion at all. The time complexity is still going to be the same, the memory complexity is still going to be the same, but let's still do this for learning purposes. So breadth first search on a tree is basically level order traversal. We're traversing each level by level until we get to the end or the last level, and then we can't continue anymore. So you can kind of see how breadth first search is a pretty intuitive way to find the max depth, right? We're basically counting the number of levels we have. So here we see, okay, we have 1 level. Next we see we have 2 levels. Oh, this is the 3rd level, and we can't go any lower. So what's the number of levels that we had? We had 3. That's the number of levels is basically going to be the same as the max depth. So now the only problem is, how are we actually going to code this up? Now, typically BFS involves a queue or a DQ, or however you call it. And so the way it's going to work is the queue is initially just going to have the root value. So I'm going to kind of represent this array as the queue. So initially we're just going to put the root in the queue, right? So now we're going to say, okay, what's the length of our queue? These are the elements currently in our queue, and these are all at level 1. So now we're going to go through every node in our queue. We only have 1, and we're going to take 3. Now we're going to remove it from our queue, and we're going to replace it with its children, 9 and 20. So let's add 9 and 20 to the queue. So now now this is our second level, right? These elements that we have here are our second level of the queue, the second level of the tree. So we're gonna do the exact same thing with these two nodes. We're gonna take the first one, 9, get rid of it. We see 9 is here. Now we're gonna replace it with its children. It doesn't have any children, so we don't have to replace it with anything, right? But we're gonna keep going. Now we're gonna go to the second one, 20, remove that from our queue, and replace it with its children. What are its children? We have 15 and 17. So let's add 15, I ran out of space, but that's okay, and 17 to our queue. Now this portion is the next level. It's level 3. So let's continue to go. So 15 is the first one. Let's pop it. Let's get rid of it, replace it with its children. It doesn't have any children, so it's a base case. Next one, 7. Okay, I wrote 17, but it's actually 7. Sorry about that. I'm not paying attention. But okay, we're gonna get rid of this 7, and we're gonna see, okay, 7 did not have any children either. So now when we continue to go, we're gonna see, okay, there's nothing left in our queue, so we have to stop, right? That's how we know we're done traversing the entire tree. When we went through every single node, what's the max level that we actually got to? Of course, it was 3. So that's what we're gonna end up returning. The max depth of this tree was 3. Okay, so now let's get rid of this and actually do that solution. So another base case, or the same base case, I'm just gonna say if not root, we can still return 0. So if there's no root, then we're gonna return 0. And we're also gonna maintain the current level that we're at, and we're gonna have a queue, which in this case is going to be a deck. And initially, we're gonna initialize this queue with just a single value, the root. I think most libraries do have a queue structure. So we're gonna initialize our queue like that. We're gonna have our level initially at 1. We're gonna keep going until the queue is empty, right? So now we want to go through the queue and remove every element that's currently in it, right? So however many are in it. So we're gonna say for I in range, length of the queue at this current time, right? So we're gonna take a snapshot of the length of the queue. Maybe it has 1 element, maybe it has 2. We're gonna take a snapshot, remove all of those, and then add the children. So basically traverse the entire level and then add the next level. And then once we're done with that entire loop, we're gonna increase the number of levels. So for every node in the queue, we're gonna go ahead and pop from the left, just like we did in the picture. We're always gonna be popping from the left of the queue, and we're always gonna be adding to the right of the queue. So we're gonna pop a node, and then we're gonna go ahead and add its children to the queue, only if the children are not null. So if node.left is non-null, then we're gonna go ahead and say queue.append node.left. If node.right is non-null, then we're gonna append that one as well. So queue.append node.right. And actually, if we're gonna be doing it this way, we should probably initialize our level to 0. So you can see that we're never gonna be adding null nodes to our queue. So every time our queue is non-empty, we can be sure that there's at least a non-empty node in the queue, right? So we're basically counting the number of times our queue is gonna be non-empty. So each time it is, we can basically increment the number of levels. And then at the end, once our queue is finally empty, we know that we have totaled up the number of levels, and we can go ahead and return that. So you can see this solution also works, and it's also pretty efficient. So this is the breadth first search solution. But there's one more solution I want to show you, the iterative depth first search solution, basically depth first search without using recursion. So now we're gonna do iterative depth first search, and we're gonna be needing a stack data structure because we're basically gonna be emulating the call stack, the recursive call stack, right? So you know, in a recursive DFS, we go to this node, right, and then we go to the left subtree, right? And when we're done with the left subtree, then we pop back up to the 3, and then we go down to the right subtree, etc. Right? That's like in order DFS. But we're gonna be implementing pre-order DFS with a stack because pre-order is actually by far the easiest one to do iteratively. So what we're gonna do is we're gonna say, okay, come to this node, process this node, right? Then add the children to the stack, the left and right children, right? Now in our normal pre-order traversal, we'll do the left subtree first. So what we're gonna do is now say, okay, let's do the left subtree. Well, we're gonna go to the left subtree. It's pre-order, so we're gonna process this. Then we're gonna do its children. Well, it doesn't have any children, right? So now what are we gonna do? Well, this one was added to the stack, so then we can go ahead and process this one and add its children to the stack. And then we're gonna process this one. It doesn't have any children, and then this one's gonna be at the top of the stack because we just popped this one, and then we can process this one, and then we're done, right? So we're gonna do that. And as we do it iteratively, we're not just gonna be adding the nodes themselves to the stack, but we're also for each node gonna be adding the depth of each node because we can easily do that, right? We know this is gonna be depth 1. When we add the left and right children, we're gonna say, okay, these are at depth 2. When we add these two, we're gonna say these are at depth 3. So we're just gonna try to visit every single node, find the node that had the greatest depth, and then we can return that. So initially we're gonna start with node 3 at depth 1 in our stack. So now we're gonna pop from our stack. So let's pop this node and we process it. So far the max depth we found was 1, and let's add its children to the stack. So let's add 20 to the stack, and let's add 9 to the stack, and each of these are 2, so we don't update the result. Reorder DFS with a stack. Okay, so finally for the last solution, so this was BFS, but now we did the result. Pop one more time. This also had a on it the root, but remember we're also maintaining because it's possible the node could be null. So if it's non-null, what we're gonna do is we want to update our result. Now initially we're gonna set our result equal to 1 because we know we do have at least a 1. And so if we pop this node and it's non-null, then we can potentially update our result. So we'll set the result equal to the max of itself and the depth of the node that we just popped. And so copy paste and update this. So we're adding both of the nodes, even if they're null, we're adding them, and then we're just gonna continue through the stack until the stack becomes empty. And then once that is done, we can go end up updating the result. So this is the third and final solution that I want to show you. They all have basically the same time and